Imagine walking into the strangest school on earth. There are no teachers at the front, no exams at the end, and the student is not asked to explain a single idea. Instead, it sees a sentence with the final piece covered up. The cat sat on the. The student guesses, airplane. Wrong. Somewhere inside it, billions of tiny dials turn by an almost invisible amount. Then comes another sentence. And another. Books, websites, code, conversations, captions. Over and over, the same strange lesson. Look at what came before and predict what comes next. At first, the guesses are nearly random. But after an enormous number of corrections, this student can write an email, explain gravity, translate a joke, and help debug software. How did a machine trained to finish sentences become something that looks as if it can answer almost anything? The word learning can be misleading. When a person learns, we imagine understanding, memory, experience, maybe even a moment when an idea finally clicks. For a language model, we can describe something much more concrete. Numbers change. A model contains a vast network of adjustable numbers called parameters or weights. Think of them as billions of tiny dials connected to one another. No single dial contains Paris is the capital of France. No single dial stores the rules of grammar. Together, however, their settings influence which token the model predicts next. A token is simply a chunk of information. It might be a whole word, part of a word, punctuation, or another small unit the model can process. Training is the process of adjusting all those dials so that useful predictions become more likely and bad predictions become less likely. That definition tells us what changes. It does not settle whether the model understands in the same way a human does. That is a different, much harder question. Before training begins, the raw material has to be prepared. Developers collect data from different sources, remove some unwanted material, reduce duplicates, organize it, and convert it into tokens. Different companies use different mixtures, and the exact recipe for many modern models is not public. Then the guessing game starts. The model receives a sequence of tokens and produces probabilities for what might come next. Maybe Matt receives a high probability after the cat sat on the. Maybe airplane receives a tiny one. During training, the real next token is known. The prediction can be compared with the answer, producing a score for how wrong the model was. Machine learning researchers call that score the loss. Now imagine every parameter as a dial on a gigantic control panel. The training system works backward through the network to estimate which dials contributed to the mistake, and in which direction each one should move. It does not rebuild the machine after every sentence. It makes a very small correction. One sentence barely matters. Millions and billions of examples do. Repeat this process long enough, with enough computing power, and the model gradually becomes better at predicting language it has never seen in exactly that form. This first giant stage is called pre-training. Here is the surprising part. To predict the next token well, the model cannot rely only on the last word. It has to notice grammar. It has to track whether she refers to the doctor or the patient. It has to recognize that a recipe, a legal contract, and a comedy routine follow different patterns. It benefits from learning that Paris relates to France, that heat can melt ice, and that code opened with a bracket may need to close it later. Modern language models are built around an architecture called the transformer. One of its key ideas is attention. Attention is like a set of movable spotlights. When the model processes one token, those spotlights can emphasize other parts of the context that are useful right now. A name from 3 paragraphs earlier. A number in a table. The subject of a long sentence. The model does not receive a handwritten rulebook telling it where every spotlight should point. Training gradually shapes those patterns too. So the next token game forces the model to build reusable internal relationships. That is why a simple training objective can produce surprisingly broad capabilities. But there is a catch. The model is learning what patterns help prediction. It is not automatically building a perfect library card for every claim. It may learn a relationship without preserving a reliable trail back to the original source. After pre-training, the model may be knowledgeable, but it is not necessarily pleasant or useful. Ask it a question, and it might continue your question instead of answering it. It might imitate a forum argument, generate unsafe material, or produce something that sounds relevant while missing your real intention. So the model goes to a second kind of school, post-training. In one approach, human trainers write examples of good answers. The model is trained to imitate those demonstrations. This is often called supervised fine-tuning. Then humans may compare several candidate answers and rank which ones are more helpful, honest, safe, or clear. Those preferences can be used to further shape the model's behavior. Reinforcement learning from human feedback is one well-known method, although modern systems can use other preference training techniques too. This stage helps transform a text completion engine into an assistant that follows instructions. But notice what the humans are supplying: demonstrations and preferences. They are not installing a magical truth detector. An answer can be polite, clear, and preferred by evaluators while still being factually wrong. Post-training can reduce some bad behavior, but humans like this answer, and the universe confirms this answer, are not the same signal. Now we reach one of the most common misunderstandings. When you tell a chatbot your name, and it uses your name 5 messages later, it feels as if the model has learned. Usually, something simpler is happening. Your recent conversation is placed inside the model's context. The model reads that context each time it produces the next response. Some products also have a memory feature that can save selected information and provide it again in a future conversation. Context and saved memory can change what the model says, but they are not the same as changing the model's billions of underlying weights. During ordinary use, the model is normally doing inference, applying the patterns already stored in fixed weights to the information currently in front of it. A provider may later use some conversations to evaluate or improve a future model, depending on the product, policy, and user settings. That is a separate pipeline. Your single correction does not normally rewrite the shared model for everyone in real time. Another popular argument offers 2 extreme choices. Either the model is a giant copy and paste machine, or it never memorizes anything. Reality is messy. Much of a model's usefulness comes from learning patterns that generalize beyond one training example. It can write a new sentence that never appeared in its data. It can combine familiar relationships in a new context. But research has also shown that language models can memorize and reproduce some training sequences, especially under conditions such as repeated examples, large model capacity, or specially designed prompts. So the model is not a database, is useful, but the model never memorizes, goes too far. The better picture is a strange compression machine. It captures enormous numbers of relationships in its parameters. Compression preserves many patterns, blurs some details, loses much of the original provenance, and occasionally retains exact fragments. That mixture explains both generalization and risk. Return to our strange school. The student began by guessing covered tokens. Pre-training shaped its internal dials. Post-training taught it how humans wanted those capabilities expressed. And during a conversation, context gives it temporary material to work with without rebuilding the student from scratch. The same learning process creates 2 very different outcomes. It gives the model the power to summarize, translate, explain, and generate. And it helps explain why the model can still hallucinate. It was trained to produce a likely continuation. It was trained to follow instructions and satisfy preferences. Neither process guarantees that every sentence has been checked against evidence at the moment it is spoken. Understanding how a large language model learns is not a reason to dismiss it as just autocomplete. It is a reason to use it with clearer expectations. Let it find patterns. Let it transform language. Let it help you explore possibilities. And when the answer truly matters, ask for the one lesson its strange school never guaranteed. Show me the evidence.